Greetings and salutations, magical chemists. Let's get trendy with periodic trends. Periodic trends are specific patterns that are present in the periodic table that illustrate different aspects of a certain element. Almost all the properties that you could be asked about on the AP Chemistry test rely on describing the electrostatic attraction, the Coulombic attractive force between electrons and the nucleus. This means you should always, either specifically or at least obliquely, mention Coulomb's law in your answers. Coulomb's law, of course, is that magical equation that says the energy of attraction is directly proportional to the magnitude of the charges that are like the positive and the negative, and that are inversely proportional to the distance between the charges. For periodic trends, often that energy of attraction that we're talking about is going to specifically be the ionization energy, which is the energy needed to remove the outermost electron from an atom, or ion. And the charges, of course, well, Q1 is the charge of an electron, -1. And then Q2 is what we're going to call the effective nuclear charge, or ZEF, which is related to the number of protons in the nucleus. The distance between the particles, or R, honestly, right, R for radius, we are approximating that as the difference, it's the distance from the nucleus to the outermost electron, the radius of your atom. But we kind of approximate that by identifying the energy level the electron is found in. The higher the energy level, the greater the distance. As you probably know, we don't do quantitative or numerical calculations with Coulomb's law in chemistry, or AP chemistry, but you do have to know the qualitative connections here. In short, Coulomb's law says that the energy of attraction between a positive and negative, or repulsion between two positives or two negatives, is directly proportional to the magnitude of the charges and inversely proportional to the distance between them. So, as I was mentioning, all periodic trends can be understood in terms of Coulomb's law, because electrons are attracted to the protons in the nucleus of an atom. So the closer an electron is to the nucleus, the more strongly it is attracted. And we approximate that distance by looking at n, the number of energy levels. And the more protons in a nucleus, the more strongly an electron will be attracted. Now, electrons are repelled by other electrons because that's the energy of repulsion between two like charges. So if other electrons are between a valence electron and the nucleus, the valence electron is actually less strongly attracted to the nucleus because of electron-electron repulsion. This is known as electron shielding. Okay, we have one last concept to discuss relative to Coulomb's law, and then we can dive into trendy trends. So let's talk about effective nuclear charge, or Z effective, abbreviated ZEF. This is the net positive charge experienced by electrons. This is basically reminding us that a valence electron, while is attracted to the nucleus, some of that attraction is blocked by the core electrons that are basically in between the outermost electron and the nucleus. So this basically says the higher an energy level an electron is found at, the further away from the nucleus, it's going to feel less positive charge overall. So the thing to remember here is that the nucleus of atoms that have a higher ZEF at the same energy level, well, higher ZEF is like a higher equivalent positive charge, the electrons are going to be more attracted to that nucleus. And that means, of course, that the nucleus of an atom that has a lower ZEF will be less attractive to its valence electrons. Something that's important to note for free response questions is that if you are comparing two different elements of the same energy level, the ZEF is directly proportional to the number of protons, right? More protons, more attractive nucleus. So many times in answers, you actually are not necessarily referring to the effective nuclear charge so much as just the nuclear charge. You just talk about number of protons and you will totally be okay as long as you are at the same energy level. It is very, very important to realize that the energy level is more important as far as determining the trend than the effective nuclear charge. The distance between the electrons of the nucleus matters more than the attraction based on number of protons. Crazy but true. So when you're comparing elements that are in different energy levels, It is the energy level comparison that matters. Don't worry, this is such an important point that we will definitely be reinforcing this as we practice our periodic trends. Speaking of trends, let's dive into our very first trend. Atomic radius, or size of an atom. Technically, it's defined to be the distance between the nucleus and its valence electrons. And the hint for remembering this trend is snowman. That's because as you go further and further down, you're adding more and more energy levels. And if you're in a higher energy level, you are further from the nucleus. So it gets bigger and bigger and bigger as you go down the periodic table, making a shape that looks just like a snowman. What's interesting, and perhaps counterintuitive, is that the size of an atom will on average get smaller and smaller as you go further and further to the right. We are in Texas, after all. Our snowman fell over. And the reason is, as you have more and more and more protons on a given energy level, the electrons are more and more and more attracted. So the trend for atomic radius is that it will get bigger going to the left and bigger going down. What's interesting is you can also look at ionic radius. This is the distance from the nucleus to valence electrons in a charged ion. Ions, of course, happen when you gain or lose electrons. So if you're trying to compare a neutral atom and its ion, or multiple ions of the same atom, honestly, electron or electron repulsion is usually the go-to explanation. If you make a cation, or a positively charged ion, well, the idea is that they are going to be smaller than their neutral atom because, well, you've stolen one or more electrons. So now, on the valence level, there's less electron-electron repulsion. And if they're less repulsed, they kind of snuggle up closer to the nucleus. They are closer to the nucleus. And by definition, that means the ion is smaller. As you can imagine, the anions, or the negatively charged ions, well, it's the opposite. They get larger. This is because adding electrons increases electron-electron repulsion. And since they're repulsed, they are thus a little bit further from the nucleus. There is only one type of comparison between an atom and its ion that should not utilize an electron-electron repulsion argument. This is when you're looking at ions, where they've either lost or gained enough electrons that they will have lost or gained an entire energy level. Usually this means we're talking about metals and metal cations, because oftentimes metals will give up all of their valence electrons. Well, that means now their valence level is an entire energy level closer to the nucleus. And as we know, the N, energy levels, matters more than the effective nuclear charge. So if your valence electrons are on a lower energy level, they are going to be closer to and thus more attracted to the nucleus. In the picture below, you can see that this is a huge difference in size. So lithium, becoming an ion, loses its entire second energy level. So it becomes much, much smaller. Same with beryllium. Beryllium lost 2 electrons and thus has lost its entire second energy level. And of course, it actually is the same. It's interesting. Now, there isn't such a dramatic increase, but it's still a pretty big increase when you go, say, from oxygen to O2 minus. It's gained 2 electrons. That electron-electron repulsion is significant. The ion is much larger than the neutral atom. Okay, on to the next trend, electronegativity. Electronegativity is basically the attraction that an atom has, or its nucleus, how strongly it's pulling on the valence electrons it has in a covalent bond. So if 2 atoms are sharing electrons, how strongly in that tug of war, who is winning? Whichever one is pulling the electron density more strongly, they have a higher electronegativity. Electronegativity is actually determined by combining 2 different trends. You look at both something called ionization energy and electron affinity. They are similar but not quite the same thing. Ionization energy, honestly, is more commonly talked about, and it is the energy required to remove an electron. So you've got something neutral, and it takes some amount of energy to steal the electron away. That, I hope you recognize, will always be endothermic, right? It's like you're not ending a bond per se, but you're ending an attraction. You're separating 2 things that are attracted, and that takes the input of energy. Electron affinity is similar, but this time it's the energy change when you add an electron. So ionization energy is energy to steal. Electron affinity is the energy change when you are forcing it to accept an electron. So in this case, you're taking something neutral and saying, here's your tasty electron, you must have it. Now, the first electron added is always going to be exothermic because of the attraction. There's always going to be some level of attraction between the electron added and the nucleus. It can be a very different amount of attraction, but some attraction will always exist. Higher attraction between a nucleus and electron will always result in a higher ionization energy. They're more attracted, takes more energy to remove, and a higher electron affinity. Ionization energy and electron affinity both match what I call the ice cream trend. If I was going to draw my beautiful periodic table, the way that I remember how this trend increases is the attraction between a nucleus and electron increases the closer you get to the nucleus. So that's going to increase more and more as you get towards the top of the periodic table. That also means they are going to increase as you go further to the right because there will be more and more and more protons in the nucleus. So that's like your ice cream fell over. You might have noticed this is exactly the opposite of the trend for atomic radius. Since we just talked about ionization energy, this is the perfect time to introduce a concept known as metallic character, or for that matter, non-metallic character. They're exactly the opposite. As you hopefully remember, metals react by losing electrons. They tend to form cations. Well, the greater your metallic character is, means the easier it is to remove an electron. So that's the key. So if you have a low ionization energy, it just doesn't take that much energy to kick off your electrons, that gives you a high metallic character. It just means you're going to react a lot like a metal. Non-metallic character is exactly literally the opposite, because nonmetals are defined as species that react by gaining electrons. So in this case, the harder it is to remove an electron, the higher its ionization energy, that's going to mean it has a very high non-metallic character. It's going to try to react like a nonmetal. So let's take a moment to practice just a little bit of these beautiful, beautiful trends. So I have recreated, very accurately of course, a small square from the periodic table of oxygen, fluorine, sulfur, and chlorine. So you're going to look at those and you are going to use your knowledge of the delicious trends, and you are going to try this, yes, on your own, to see what you think. Out of the 4 elements shown, which element would have the highest ionization energy, the highest electron affinity, the highest metallic character, and the highest non-metallic character? Go ahead and give that a try, and when you're ready to check, unpause the video. All right, these questions didn't ask you to explain why. Shocking. Just identify the general trend. So what I like to do is I'm looking at things like ionization energy. I like to just remind myself what the trend is. And ionization energy is the ice cream. It gets bigger going up and bigger going to the right. So if I want the highest ionization energy, good old fluorine. But that also means it has the highest electron affinity, which makes sense, right? Fluorine loves to steal an electron and become fluoride, and much less dangerous. So the highest non-metallic character would definitely also be fluorine, because it has the highest ionization energy. But that means the thing furthest away from fluorine, in this case sulfur, would have the highest metallic character. Because out of the 4, it is the one that would be the easiest to remove one or more electrons from. All right, we're going to continue on our ionization energy roll here, because it turns out of all the periodic trends, ionization energy probably has the most different things that we can use it for or be asked questions about. So it turns out there's something known as successive ionization energies. That means, well, okay, the first ionization energy is when you remove 1 electron, but you don't have to stop there. Then you could remove another electron, and another, and another, and another. So we like to refer to the first ionization energy. Honestly, when people are like, oh yeah, the ionization energy high or low, If they haven't specified, they're almost talking about the first ionization energy, the energy required to remove the first or the highest energy electron, the one that's easiest to remove. The second ionization energy, well, no surprise, that's the energy it takes to remove the second electron after you stole the first. It is absolutely essential to remember it will always take more energy to remove another electron after you've already taken one away. So the first ionization energy, whatever it is, high or low, the second ionization energy is going to be more than that. The third is going to be even more. As you take electrons away, there's less electron-electron repulsion. So the remaining electrons are closer to and more attracted to the nucleus. So it's harder to steal them. Now, there is another interesting trend that shows up here, and hopefully this makes sense. Valence, the outermost electrons, definitely require less energy to remove than any of the inner or core electrons. And that's all about the energy level, because valence electrons are at the highest energy level. They're the furthest from the nucleus, and according to Coulomb's law, they're less attracted, require less energy to remove. This leads to an interesting pattern you can use. If you have the information of successive ionization energies, like we do on the table down below, notice, like we're looking at aluminum. Here's its first ionization energy, second ionization energy, so on and so forth. You'll notice they're always getting bigger. You're like, oh, it's almost 3 times as much. Okay, that one didn't quite double, but it got bigger. There will be this giant leap upward to a much, 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 much higher number at some point. That's a sign. And that big change in energy, you must have removed all the valence electrons, and now you're trying to remove a core electron. So you can determine the number of valence electrons by looking at the electrons that were easier to remove relative to those ones that take more energy to remove. So that's how with this one, now to be fair, we know it's aluminum, so we know it's going to have 3 valence electrons, but you can see it from the trend in ionization energies. So let's go ahead and give that a try. These questions are pretty common on the AP Chem test, but luckily, if you recognize the pattern, they're pretty easy to figure out. This one says, well, what element from period 2 does this table of successive ionization energies represent? Well, we don't know the element, right? We don't know how many valence electrons, but we look at the pattern. And so you're like, okay, this is, pretty big jump here, pretty big jump here. Oh my God, a ginormous jump here. Okay, well, sweet. That means there must have been 3 valence electrons. You might be thinking, wait a second though, the 3 valence electrons, there's a lot of atoms with 3 valence electrons, but they were specific. They said these are all in period 2, or row 2. And the only thing in row 2 with 3 valence electrons is delicious boron. Now, you do have to be able to explain this, but it's basically just explaining the pattern. Always start by answering the question. So this is boron, and then explain. Well, we know it's boron because its 4th electron requires significantly more energy to remove than the first 3. Careful though, you have to connect that. Okay, but how does that tell you it's boron? Well, that means it must have 3 valence electrons. Okay, there are other free response problems they can ask you about successive ionization energies. Sometimes they won't directly say successive ionization energies, but if you recognize the pattern, it can make it a little easier to answer the question. For instance, on number 2, it says, would it require more energy to remove an electron from an F plus ion or an F2 plus ion? Well, notice you removed an electron from fluorine and now you're removing another. So technically, if you're looking at fluorine, you're starting with fluorine, and originally you would take 1 electron away. So the energy it takes to get to F plus would be your first ionization energy. But they're saying, okay, I want to take an electron from F plus. Well, that would be the second ionization energy. But I also want to see how much energy it takes to take an electron from F2 plus. That'd be the third ionization energy. So really what they're asking you here, and you don't have to define it this way in your answer, but it can be helpful for understanding, is you're comparing the second and third ionization energies of fluorine. And hopefully that can help you remember the trend. It will always take more energy to remove the next electron. Let's take a look at how you could explain why. First step, always answer the question asked then explain. So it would require more energy to remove an electron from F2 plus than F plus. And now we explain. Well, removing that first electron from F plus decreases electron-electron repulsion. Okay, as far as an explanation, you're like, well, it's because after I've removed this first electron from F plus, it decreases electron-electron repulsion. And the key here is, if you have less electron-electron repulsion, your electron cloud shrinks. Then, when you're taking that next electron from F2, the electron you're taking is closer to the nucleus, it was more attracted, it takes more energy. Periodic trends free response questions are very specific. It is essential that you connect the Coulombic attractive forces, this whole idea of the electrons getting closer to the nucleus and more attracted, to the thing you're measuring, which is ionization energy, or the energy needed to remove an electron. All right, turns out there is just a little bit more that we need to know about ionization energy. In general, ionization energy has the ice cream cone trend. It gets bigger as you go up to the top of the periodic table, and it gets bigger as you go further to the right. However, when you are looking at the side-to-side trend, the going to the right trend, it mostly gets bigger, right? That's the general trend. Whoops, I don't know what I just did there. Hey, look, I drew an arrow. Well, the idea is that in general, that's the trend. It's getting bigger and bigger and bigger along the same energy level. But you probably noticed it didn't just quite go up. There were these two glitches. So we need to know those glitches and what causes them. The first glitch happens when we're comparing groups 5 and group 6. We call this the P4 glitch. Let's take a look at nitrogen and oxygen and their P sublevel to see why this is the P4 glitch. Looking at your periodic table, you can see that nitrogen only has 3 electrons in its 2p sublevel. So if you were writing its electron configuration, it would end with 2p3. Oxygen, however, has one more. 1, 2, 3, and 4. Did you notice the first 3 were all unpaired? They had a room of their own. But, when you added that 4th electron, now you have 2 electrons occupying the same orbital, and electrons repulse each other. This is the P4 glitch. You would think, based on the fact that oxygen has more protons than nitrogen, it would be harder to remove the first electron from oxygen, but it's not. And that's because of the repulsion of the paired electrons. So when you're graphing ionization energy, nitrogen actually has a higher ionization energy than oxygen. Weird, but true. Okay, the second glitch is called the S2P1 glitch. This is looking at the difference between group 2 and group 3. To look at this glitch, we can compare beryllium and boron. Well, you'll notice that the last electron placed, the one that we stolen for your first ionization energy in beryllium, is one of the 2s electrons. But in boron, that last electron placed is in 2p. So we're talking about an s sublevel versus a p sublevel. And even though boron has more protons, the difference in shape between an s and p orbitals means that the s electrons are actually more tightly held. If you look at a graph of electron density, where 0 would be the nucleus, well, the idea is if you're in a p orbital, there is a lot of electron density pretty close to the nucleus. But s orbitals are interesting. They've got this node that's very close to the nucleus and then a whole nother one. So on average, an electron in 2s or 2p is about the same distance from the nucleus, but because of this electron density that's basically snuggled up close to the nucleus, it makes it harder to remove an electron from an s sublevel because, the attraction is between the nucleus and the valence electron. This is unfortunately known as nuclear penetration. p orbitals do not penetrate the nuclear region as much as s orbitals, so the p orbital electrons are easier to remove. So there are supposed to be arrows down here. They somehow turned into boxes. So that's supposed to be an arrow, and just one arrow. Okay. So it's not about distance, but it's about the location of the density. So that is why it has its own special term. All right, so that was our other glitch. So let's map out the ionization energy trend. We already know that in general, ionization energy follows the ice cream trend. It gets larger as you go closer to the top of the periodic table. Now that will always be true. That's just a thing. The questionable one is the fact that it gets larger as it goes from the left to the right. Well, that's mostly true as long as you remember the glitches. All right, that is the end of the things that we need to know about ionization energy. And we have one last trend to talk about, reactivity. Now, reactivity is a really generic term because reactivity honestly depends on, are you reacting by losing electrons like a metal or gaining electrons like a nonmetal? Well, since metals are more reactive, as it's easier to take away their electrons, metals become more and more reactive as you move down a column on the periodic table. That's because there's less attraction between the valence electrons and the nucleus at that point. Lower ionization energy, more reactive metal. As it's probably unsurprising, nonmetals are the opposite. Nonmetals are less reactive as you move down a column because they gain electrons in their reactions. And it's harder and harder to gain electrons as you have more and more energy levels the further down you go on the periodic table. Whew, all right, that was a lot of trendy trends. Let's take a quick moment to make sure that we have the basic pattern, and then it will be a great idea to try some practice questions to reinforce this. But first, let's remind ourselves. So we are going to go ahead and draw arrows that basically they're pointing in the direction that each trend increases. Atomic radius or size, well, they get bigger. This is the snowman trend. They get bigger as you go further to the left and further down. Metallic character is, I think, the only trend that matches atomic radius, because metallic character is how easy it is to lose an electron, and the bigger you are, the easier it is. Electronegativity and ionization energy are both the opposite, because electronegativity and ionization energy both increase going up and increase going further to the right. Now, both of these have their own exceptions. We didn't mention the electronegativity trend, but I just want to throw this in there because it's important. Electronegativity is how how strongly you're pulling on electrons in a shared bond. But noble gases don't bond, kind of. So they generally have a very low, indeed even non-existent electronegativity. Ionization energy, as we know, has the S2P1 glitch and the P4 glitch. Last but not least, we have the reactivity trend, which is different from metals and nonmetals. Metal reactivity increases as you are going to the left and going down, but non-metal reactivity is the opposite. All right, so those are the basic trends you need to know to be trendy. In the next video, we'll talk about how to answer free response questions about periodic trends with enough specificity to gain lots and lots of points on your AP Chem test. Thank you for playing with periodicity and all of the glories of chemistry.